And hello friends, welcome everyone to this video. This video is basically talking about some MATLAB scripts and they pertain to frequency response. Okay, some tools for frequency response, for example, fast Fourier transforms, how to import CSV files. These are very basic, okay? It's just, okay, yeah, I was developing some projects and I just needed to use some of the code. So yeah, this video basically just does an overview and I have the bits of those codes on GitHub. Okay, where do you find it on GitHub? Look for MATLAB frequency response under my repository. Under my username. I'm on Git. Okay, so MATLAB frequency response.git will be the one you're looking for. Okay, so why am I using Ubuntu? Okay, I'm actually on Manjaro now. I'm using Ubuntu virtual machine because MATLAB tends to work better with Ubuntu. You can use Windows or whatever as well. Should be more or less the same steps, at least in a more conceptual sense. Okay, it should conceptually be the same. Okay, so how do I start MATLAB here? I just put MATLAB dot. I start MATLAB in there and I use the N button. So the dot is just to start it in this folder. So MATLAB should start up. Alright, so what are we trying to do here? Okay, I have a lot of code, but what are we trying to do here exactly? Alright, what we are trying to do, okay, let's open this up. Okay, so basically we have two sets of data, right? Let me take a GIMP. Oh, oopsie. Yeah, we have two sets of data. Okay. So basically, we have a system. We have a system G of S with some of the transfer function. It will give some output based on some input. Okay, I of S. So this is basically what we are doing here. You should be familiar with all this terminology. If not, do go brush up your theory. I'm not going to go through all of this. Okay. Or you can just search it elsewhere on YouTube, where there should be a lot of explanations of what these are. Basically, what you have is basically you're sending some sort of a signal through a system. Okay, it can be a sine signal, cosine, or a superposition of such. Okay, a superposition of such, and the system will respond in kind. If it's a linear system, it should give you a sine output as well. Okay, so basically, let's say you perform the test. And now you have some sort of data, right? You have time, input, and output, right? So normally your Excel data or whatever, it can be maybe at 0.1. I have input 1, so I1, and then I have output 1. Output 1, not output I. Okay, maybe at time 0.3, you have input 2, it will be a different signal, and then output 2, maybe 0.4. Okay, input 3, output 3, and so on and so forth. These may be sampled so-called randomly, depending on what your program is, how you generated this data. Okay, and what you're trying to do is you're trying to find, okay, what are the frequencies here? What are the frequencies in your input and output? Okay, so you have a CSV file. So all these are in CSV form. So you want to try to find the frequencies of these inputs and outputs, right? And you basically want to do, in frequency response, you kind of want to find the gain and the phase shift, right? The gain and phase shift. Okay, especially if it's a linear system. Okay, so how are you going to do that? Okay, so this video is going to go through some of that. So, like I said, here we have some input and output. I'm going to save this as an ODS file so that I can actually plot things out for you. Take a look at what it looks like. All right. Okay, I'll save it here. No, I'll do it here. Yeah. Oh, no, I want to do it here. Come on. Here. Save as. I'll just put it here. Anyway. I'll put the ODS under ODS and save. Now just shift it to the desktop. Okay. Alright, so I'm just gonna, now these are actually lots of pieces of data. You have like 10,000 seconds worth, almost 3 hours worth of data. So basically I have an input and output signal. Okay, for frequency response, it usually is a voltage. It can be a voltage signal, power signal, whatever you have. Okay, let me insert a chart. Okay, insert chart. Let me use scatter. And I'll just quickly finish. I'm not going to give you axis, but this is basically what it looks like. Alright. So you'll have your input, which is in blue, output, which is in orange, and it looks very messy. So what you can do is just maybe use less points. Okay. Delete this. Yeah, so maybe I'll just use half the data or somewhere till 4,000, then that's enough. Okay, so let's insert a chart again. Now quickly go through what it looks like and finish. Yeah, so this is what the data looks like. I use a reduced set of data. So basically my input signal, whatever it is in blue. My output signal is in orange. Okay, how can you use MATLAB to distill down this data? Which means I want to find maybe the phase, but the phase of this input signal over here. This is the input signal. Okay, I want to find the phase and let's say amplitude, for example, of this input signal, phase and amplitude of this output signal. Okay, how do you go about doing this? Okay, or rather, yeah, when it comes to frequency response, the absolute amplitudes and phases are not as important. What we want to find is the phase change and the gain in the gain in the amplitude, right? So what you want to do is to use some of MATLAB's tool to do that. All right, so this is the example I'm going to work on. Okay. I'll walk you through some steps and some of the functions that are being used. Okay, so all right, what do you need to do first? First thing first, before we start, let's go through some sort of a overview, right? Okay, so we have this CSV data. We actually want to do something called a fast Fourier transform on it. Fast Fourier transform. Okay, and then we want to find the gain and the phase, right? The gain and phase. So how are we supposed to do it in MATLAB? Okay, so first thing first, we need to import the CSV file. Okay, your first step is always to just get your data into a MATLAB array form, right? So how are you supposed to import it? So let's go to MATLAB. Okay, this one is not that difficult, but anyway, in case you're wondering, this is how you do it. First thing first, you use this function called readtable. Readtable actually takes, okay, readtable actually takes a CSV file. It can also take an XLS, ODS file, or spreadsheet file for that matter. But I just prefer using CSV because for sure, you know it's only comma separated values or CSV. There are only data points there. So yeah, that should be, I think, what you want to work with. Okay. So I'm going to start a new script or something like that, but the completed script is here, and you can see what I'm doing. Okay, but first thing first, your thought process is, okay, I need to import in a CSV file first. So let's import in a CSV file. What's the CSV file we want to import? It says data frequency 2e minus 3. So that's 2 times 10 to the minus 3 hertz. Okay, that was my so-called data set for a project. Okay, so let's do read table. Okay, so the command is read table data. Okay, I'll need to open the parentheses or apostrophes or whatever. Okay, data freq 2e minus 3 dot CSV. So remember to put everything there and close. So read table data freq 2e minus 3 CSV. So once you do that, this is what will come out. Okay, this is a table. This is not yet an array. Okay, but it does look like an array. So you're kind of halfway there. So to actually start doing math with MATLAB, you actually need to convert this to an array format. Okay, so when you do this read table thing, it will churn out an answer, and basically whatever you have in your CSV file, you have one column for time, one column for this case is an inlet temperature because it's an industrial process. So I have an inlet temperature and an outlet temperature. So I'm trying to do some frequency response with that. Okay, so inlet temperature is varying with time. Outlet temperature also varies with time. All right, so I have this data actually put into 3 columns, which is great. All right. However, it's inside the answer, so it's inside the MATLAB workspace as an answer. So what I want to do is to convert this to I want to store it as a variable under table. So table, okay, if I just restart, instead of using read table, just using the read table thing there, I can put table equals to read table again, data freq 2e minus 3 dot CSV. Do it exactly like so, word for word, and you should see that your table here will have all of these. Okay, so now let's say I want to find the difference between the outlet temperature and the inlet temperature, for example. Okay, just for example. Okay, so inlet. Okay, inlet equals to table the all rows. That's why I use this colon down here. All rows, comma 2. Okay, so this should contain all the data of the inlet temperatures, which is great. Okay, outlet equals to table column 3. Okay, column 3. So I use the colon to denote that I want to select all rows, and I use column 3, which is over here, the third one. So for MATLAB, we start from row 1, row 2, row 3. Sometimes for Python or C++, you may start from row 0, but here in MATLAB, it's a little bit more intuitive. So, okay, so we repeat the process for this outlet temperature. So let's say I want to do subtraction, right? I want to do subtraction. So difference equals to outlet minus inlet, for example. Okay, what will MATLAB say? Operator minus is not supported for operands of type table. What does it mean? You cannot do mathematical operations on tables. You need to convert them to an array. So your second part will be using this table to array function, which converts a table to a homogeneous array. Okay, so it will convert everything to a homogeneous array. So table equals to, or if I were to be a bit more specific, array equals to table to array. And what do I want to use this function on? I want to use it on my original table. Okay, and what can I do in my array now? Okay, so now it's literally just data and numbers over here. There's nothing else. There's no header or anything, so it is like a legit array. So let's repeat again. Inlet equals to array. Now this time I'm doing it with the array, so column2, and outlet equals to array column3. So I'm using the colon to denote that I want to have all the rows selected, and the second one will then denote, alright, I want the third column. Okay, so this is going by how MATLAB works. Is you define the row then define the column for any array you use. Okay, I'm sure you should have known by now. This is basic MATLAB knowledge. So I'm assuming you have a little bit of MATLAB knowledge by now. Yeah. Okay, so now I want to do my difference calculation. So outlet minus inlet, and there, it will work. So the first part of getting your stuff in, okay, getting your what do you call that, data in from CSV is to use these two functions. Okay, readtable and table2array. Okay, so what is your next step? Okay, you then need to do fast Fourier transform. So I'm going really quickly. All right, but hopefully the last two parts are okay for you. So your third part is to do a fast Fourier transform. Okay. Now, it is not always the case where you have data spaced within like 0.5 or very even segments. Okay, it's not always you have data at like 0.5, 1.0, 1.5 ... right? It will not always be the case. Sometimes your data may be spaced differently depending on when you sample. Okay, so normally Fourier transforms are good to deal with. They are designed to deal with data with evenly spaced time intervals. Okay, yeah, normally Fourier transforms are supposed to deal with data of evenly spaced time interval. But it's not always the case that you're going to have that evenly spaced time interval. So to generalize, what you can do is to use this function called, okay, the function is called non-uniform fast Fourier transform. Okay, so if your data doesn't happen to be sampled at equal time intervals, you can use this non-uniform fast Fourier transform to help you deal with it. Okay, how does the non-uniform fast Fourier transform work? Okay, so the usage is pretty simple. Okay, you just have a new FFT, non-uniform fast Fourier transform. You have your column vector x. Okay, what is this column vector x? Column vector x is basically, all right, your data points, right? Let's say your inlet temperature, your inlet voltage, or whatever. That will be what your column x is. Okay. Then the next argument you put in is just t. T is, let's say, your time interval. Okay, time interval, which is 0.5, 1, 1.52 for this case. Or for your case, it may be sampled at different time intervals and sampled non-uniformly. So this one samples, these intervals are sampled at 0.5 seconds. But in case yours is not, you can always just put whatever time you want. So if you have a time versus a reading, you can just put this one is like your so-called y coordinate, and this one is your so-called x coordinate. All right. So Fourier transform should be pretty straightforward. Going by this, so let's say Fourier of input. All right, I want to use my time. Okay, a time column vector. So let me use a column vector for time first, and I'll define it as array, and I'll use the first column. All right, so okay, Fourier input equals to new FFT. Okay, I use my inlet variable. or inlet array, and then the inlet data array, and I'll put time as the outlet, as the time value. Okay, so after that, your non-uniform fast Fourier transform will be finished, and you'll see all of this data out. And you notice they're in complex numbers. Okay, there's a real part and an imaginary part. Okay, before I go, I just want to illustrate why it is in a complex number again. Okay, let me use a different color, maybe a blue, a bluish color. Okay. Okay, I guess that will do. All right, so what's actually going on here? Okay. So let's say you have a wave. All right, a sine wave. Okay, and when you take the FFT, okay, fast Fourier transform, you will get the frequency omega, right? Omega. Okay, and now of course you can actually get some sort of an amplitude there because you kind of integrate it across the whole of time. All right, no problem. So yeah, I assume you know what fast Fourier transform is already. Okay. All right. So why is there an imaginary part and a real part? So in case you're wondering, just to revise, let's say you have 0.1 minus 0.2 I. All right. So what is this actually? So if you were to take a look at your real and imaginary axis, your imaginary will be your vertical, your real will be your horizontal. So 0.1 will be 0.1 in the real, and minus 0.2 is here, and you will have your points somewhere here. Okay, so this is where your point is. Okay, what is the point of putting all this? Okay, so normally when you have a sine wave like this, you can describe it as a sine omega t plus phi. All right, where phi is some offset, so you don't really start at 0 degrees. You can start at some other point in your oscillation, right? Your initial condition may not be 0, it may be somewhere else. So this phi is so-called phase, the wave phase. And how then do you capture this data? So what Fourier transform does is that it will plot something against the frequency here. It can be angular frequency, or you can even plot it in hertz, whichever is fine. Okay, I prefer plotting in hertz anyway. So you have a frequency spectra, blah blah blah. Okay, so maybe for some certain sine waves, you will have a very big amplitude. Certain frequencies of sine wave, you have a not so big amplitude. So this one will be in your frequency over here. Okay, amplitude will be actually denoted by your peaks. Okay, and where do you find your amplitude? The amplitude will be the magnitude. Okay, it will be the magnitude of this complex number, which means you take the square of 0.1, square of 0.2, and then you square root it. Basically, it's the length of this vector. Where do you find the phase? Okay, so this is the amplitude part. You take the absolute value of this complex number. The phase part, you actually take the angle. Okay, that's why you have this imaginary number and the imaginary part of complex number. So what you do is you just do your arctangent, right? Inverse tangent of your imaginary part over the real part. All right, and that's all. Okay, so well, yeah, normally for Fourier transform, the intuition is that you're separating out the frequencies of all your sine waves, but and what you normally see in your Fourier transform plots is that you'll see some sort of magnitude, okay, magnitude versus frequency. So some sine waves are more prominent, other sine waves not so much, okay. But then you're wondering, okay, where does this imaginary number come from? Okay, so this imaginary number is here to capture both the magnitude and the phase data of this wave, of this sine wave at a certain frequency. So just remember, when you see complex number, don't panic or anything. It just means, okay, it stores the phase data and it also stores the magnitude data at the same time for that particular frequency. Okay, so this is just a recap brush up on some of the basic theory in case you want to like go through all this quickly and you're like, okay, what's going on here? So this is what's going on, just a recap, and that's all I have for you. Thanks for watching.